Okay, we're going to talk about the product rule and adjust it slightly from what you may have learned before. So say we have a function f, which is the product of x and y. So that would look like df dt equals derivative of the first, dx dt, times the second, y, plus the derivative of the second, dy dt, times x. So there's a big problem here, which I've circled, which is that this works fine if they're scalars, but if these are vector or matrix quantities, like we're going to deal with in this class, we cannot arbitrarily switch the order of these operations. So it's important actually that we keep the order. And you may say, fine, we'll just rewrite this and make sure that we preserve order. So dx dt times y plus x times dy dt. So now suppose we have a function that's more complicated. Say g of t is a product of three functions, x times y times z. Usually we would have to group these into pairs. So we would say, for example, dx dt times y times z plus x times the derivative of y times z. And then we would basically apply the product rule again and say dy dt times z plus y times dz dt. And we can multiply this all out. So what you'll notice is that there are three terms, each with x, y, and z, but in each one, a different part has been differentiated. We can take this and basically twist what we know as the product rule into what we're going to call the good product rule. And it applies for both simple and complex functions. So say we have a much more complex function, a product of four functions of time, w, x, y, and z. So what we're going to do is compute df dt by doing each derivative in turn. So first we'll have dw dt, and then we'll just multiply by the remainder, x, y, z. Then we're going to do the derivative of the second term, but we're going to preserve order. So we're going to do w times dx dt times y, z. And we'll do the same thing for the third one. So first we'll write down w and x times dy dt times z. And finally we'll do the same for the fourth term. So we write down wxy times dz dt. So there you go, in one line I've written down the derivative of this complicated function by just taking the derivative of each piece of it in turn and keeping the other terms in order. So then the important takeaway here is that by applying the good product rule, the ordering is preserved, which is important for vector and matrix operations that we're going to do. And of course, it's easy to write down in one line, as opposed to repeatedly applying the product rule with only two terms and then having to pair terms together. So now you might ask, what about the quotient rule? Is there a good quotient rule? And I'm going to say no. If we have a function f of t equals x over y, remember we can always rewrite this as x times y to the minus 1. So let's do an example. G of t is going to be x plus 3 over x squared. So instead of applying the quotient rule directly, first we'll rewrite it as x plus 3 times x to the minus 2. We've just inverted x squared. So then, to take the derivative, we just apply the good product rule. dg dt equals derivative of the first term, which is 1, times x to the minus 2, plus the first term, x plus 3, times the derivative of the second term, which comes out to minus 2 times x to the minus 3. There we were just applying the power rule. So we rewrite this and get 1 over x squared plus minus 2 times x plus 3 over x cubed. So the takeaway here is we should always rewrite quotients as products and then apply the good product rule.